I'm going to start off with a basic question for all of you. Basically, could you describe core differentiating aspects of your particular approaches to AGI, why you think it'll work for human level AGI, and in particular, I want if you could address what are unique elements of your approach and why any unique elements why you think those elements would be crucial to actually implementing AGI. So I don't know who would like to go first. Arthur, you're on the screen, maybe.
Okay, sure. So can I be heard well? Everything's fine?
Good here.
Okay, great. So, I mean, being on a panel like this, having a big question pathways from here to AGI is very humbling. And that's a huge question. And I think everyone who claims to know how to do it is vastly exaggerating, overestimating his capabilities, I guess. But all I can do is to line out a little bit what is, as you said, different in my approach that we have developed here. What is specific about it? So I essentially go into the footsteps of the theoreticians first, like Kolmogorov, Solomonov, and Marcus Hutter, who has developed a strong theory of AGI. So that's, I think, the distinguishing thing is that actually, to the best of my knowledge, this is the only strict mathematical theory of AGI that we actually have, and that actually shows that you will have an agent that will be able to achieve essentially arbitrary goals in a wide range of environments, which is, as many people agree, can be a definition of artificial general intelligence. So, and having a proof like that is actually a good support. That, of course, does not mean that you have a guarantee that you will succeed, because there are troubles with that theory. And so we have taken it a step further to, essentially the idea is that you compress data, and if you can compress data, the Solomonov induction guarantees that you can predict how your future will develop in the environment that you live in. And if you can make such successful predictions, that means that you can actually pick the actions that will lead to desirable outcomes if you can make successful predictions. So that's the AGI model in a nutshell. And what we have done on top of that is to develop a theory of data compression, because compressing data is the main part of Solomonov induction, which is the ingredient to the theory. And that theory of incremental compression actually gives us hope to, or support, also mathematical support, to actually try to build a compression algorithm that implements that theory. So that's what we have been doing for the last couple of years, building the system William that compresses data and shows little tasks, demonstrates that it can solve small problems in AI. It shows intelligence to some extent, and the most recent update, I think, is since last year, is that we have actually moved to using it on practical data science tasks. And since it has shown that several machine learning techniques are actually a special case of a general compression algorithm. So, and since machine learning has been so successful, it can be, it's very promising if you have a system that actually, where the special case of its operations are various machine learning algorithms. So, I mean, that's maybe in a nutshell. And further support, I would think, is which is kind of the third pillar of the present approach, is that intelligence requiring compression or based on data compression is psychologically quite plausible. So I can go through several examples, but I'm not sure how much I can talk here now, or maybe others should give their answers too, and then we can go make some sort of a back and forth.
Yeah, this was just kind of an overview to begin with, and then hopefully we can actually engage into more of a discussion.
Yes, I thought so too. Mm-hmm.
So I don't know who wants to go next, Pei or Alexey. If no one chooses, all.
Okay, if Pei is not going to be next, let me try answering your question. I hope more shortly. Well, what's the core differentiation aspects of my approach? Well, is that I don't have actually an approach. I mean, no particular approach seems sufficient to me. And I don't mean that we should just naively combine diverse approaches. There some will not work. Cognitive synergy is like not a union, but a tensor product of approaches. But the product of a bunch of predefined approaches is also insufficient. I mean, universal methods cannot be efficient, and non-universal methods are not general enough. We have how many tasks with very different properties. Optimal algorithms can be found and proven for many of them. And we'd say that AGI is a system that can find these algorithms at least. But even in such simplified cases, when we can find these algorithms, the classes of algorithms are very different, and they cannot be efficiently found by one method. So we should have a sort of hierarchy or a partial order of methods for different generality and efficiency, which is not predefined, but extending itself. Of course, it should contain some predefined methods because we don't want to try creating AGI, but by repeating the whole evolution of the universe, right? So, okay, if you consider it as a sort of integrative approach, its main differentiate aspects are first, it's sort of omnivorous. It can eat any other approach, digest it, and make it a part of itself. Of course, if it is not just, this would be the whole story, then indeed we would say that there is no approach at all. It's just promiscuity. So the second is that our approach seeks a unifying framework. It's not just integrative, but it's cross-paradigmatic. There are aspects from different approaches like universal induction, probabilistic modeling, deep learning, metacomputations, and others that complement each other and form a holistic picture. So we seek different components which are missing in different approaches and which can be used to overcome these limitations. It's a sort of cognitive synergy, but it goes a little bit deeper on a conceptual, on a framework level. So if not going into detail, maybe that's an answer, I hope.
Okay, thank you, Alexey. Pei?
Yeah, here. Being the last speaker, I think I have the advantage of omitting the part I agree with the others and stress on our difference. I think, so first, for those who don't know, my project is called NARS, And we actually had in the first day, we had a whole day workshop and tutorial. And also, in the chat window, I post 2 files. So that's actually 2, both of them high-level roadmap. The first one was present at 2006 in the very first AGI workshop in Washington, D.C. And the second one was present last year in the previous AGI conference. So that gave you a more detailed description about the overall plan. You'll see that over those years, the plan basically remained the same. So what's the difference? The major difference, I will say, there are 2 things. Of course, technically, there are a lot of technical difference. The first difference, also the most important one, is the goal. I have said several times in the AGI conference, including the first one in Memphis. I made the claim. I know that many people doesn't really like it. Okay, what I said is we are not working on the same problem. We are working on a set of closely related problems, but not exactly the same. Why I make that claim is because, for example, as you can see from the previous 2 speakers, as well as many other people in the conference, I think that most of people in the community is still seeing intelligence is defined by the problem-solving capability of a system. We take a different opinion. To me, intelligence is not what problem you can solve or how well you're doing in solving it. It's in how you solve a problem, or under what restriction, in what environment you can solve a problem. For example, if you can solve some problem perfectly, you can beat the best one in the world in a certain domain, like AlphaGo. Okay, to me, it's not intelligent, not because it's not general enough, and also because if you always do the same thing, for example, let's say for some problem, we actually have power, enough computational power to solve it perfectly by exhaustive search. Okay, we can find many such relatively simple problems. To me, it's not intelligent at all. Not low intelligence, okay? I say zero intelligence. Because according to my working definition, which I have repeated many times, to me, intelligence means 2 things. First, it means the system must be adaptive. Second, it means the system must be able to work with insufficient knowledge and resource. You never have enough knowledge. You never have enough time. Under that condition, what you can do? Whether you can solve it perfectly, of course, under that condition, by definition, you cannot solve anything perfectly. Okay? But to me, that's where intelligence show up. If you have sufficient knowledge and resource, you just use computation. So to me, intelligence and computation complement of each other. They're used in different domains. So that is, I think, the most important difference that distinguishes NARS from many other systems in the field. So that's the goal. Okay. I'm saying we are completely different, but the stress clearly is there. For example, in this conference, I present the paper on real-time system. I said, according to this opinion, every AGI system needs to work in real time. In a sense, we say a human mind work in real time. Okay, to many people, that's kind of like too strong a claim. But to me, that's part of the definition. So you see, I just want to show, hopefully you can see the difference. The second one is a little bit technical, is how to do it. Okay, that is, for example, if you compare NARS and OpenCog, you will see that clearly. In NARS, my approach from the very beginning is to use a single technology, okay, which many people think that's crazy. Okay, that's not going to work. We're use reasoning to do everything. But of course, we're use extended interpretation of reasoning. We are using a special type of logic. We are not using several technology and try to achieve an integration or synergy or whatever you call it. To me, that's the two major difference. Everything else derived from it, and we can go back to those details if people are interested. That's it.
So, Pei, that brings up kind of an interesting question that was posted. And basically the general question is, does DNA contain language in a general sense that it has a kind of intelligence? Obviously, this might also come to your point about real time, and that DNA evolution is over many generations, but that is maybe not so fast real time, but it is some sort of time frame there. So I'm just wondering, and then open it up to discussions between everyone, but that question just came up, so
Yeah, a quick answer is, as always, yes and no. Okay, the yes part is you'll see we are building meta logic into NARS. We do not expect NARS to learn everything. We have a logic designed by me and built into the system by our team. Okay, that thing is not learned; it's innate. So in a sense, that's like the DNA. So that DNA allows the system to show intelligence. So that's the yes part. The no part is NARS from the very beginning is not trying to simulate the human brain in detail. To me, human intelligence and machine intelligence are two different forms of intelligence, and their similarity at a much higher level. That is what I said, the working principle level. Okay. At that level, I will say NARS and the human mind can be compared. For example, I fully believe that human intelligence is also show up with as a form of adaptation, and also it can work with insufficient knowledge and resource. That's actually what distinguishes it from today's ordinary computer system. Okay? But no, I'm not making any attempt to make a detailed comparison between our system with a biological form of intelligence.
So maybe let me kind of speak about a common theme that we three have actually mentioned. I don't know how to answer the question that somebody asked, but I think that will be an interesting parallel. So Alexey mentioned the trade-off between generality and efficiency. Pei has mentioned working with insufficient knowledge and resources, and I think and it's a very important point. And from my perspective, the way to approach this is actually when you usually do some exhaustive search or some optimization algorithm, it looks into in a large space, and but most elements in the large space are not likely to be the correct solution, because the correct solution is a priori has a short description. That's what Solomonov induction actually implies. So what you shouldn't do is actually, you should not do this exhaustive search. You should do a search that is highly biased towards things that can be shortly described. And for example, if you want to look up in your memory and you have some semantic network, you want to look up things that might be useful in your current situation. You want to bias your search toward those things that are quickly accessible. So maybe only one or two or few steps in the graph of your association network that leads from the current situation to the stored items. So I think this is kind of a parallel towards working with insufficient resources, and also relates to the trade-off between efficiency and generality, because it's not you will not be able to search through the whole space, but you will be still general enough to work in our world where the correct hypotheses are severely biased to be the ones that can be described with a short program. So maybe that's kind of a common theme that that may be worked out, and we can also stress the differences, of course.
Well, if we are going to switch to the topic of differences, first of all, it seems that I have to agree with Pei on that, that we are really working on different goals, because I'm actually not satisfied with a solution which can work only with a limited amount of resources, because it's quite good to have brute force solutions where we can apply them, or if even when a human is playing chess, they don't do real-time moves. So yeah, there is a quick chess and so on, but they can sit and think for minutes, and some problems are being solved for years and centuries. So it's difficult to say that they're real time, and I'm interested in such solutions which I mean solutions not to concrete problems, but to AGI, or maybe I shouldn't call it AGI, because it seems that we have different goals indeed, and if you call all these things AGI, then we have a sort of confusion. So what type of system I am interested in is a system which will be able to solve all these problems. Yes, it's my goal. It seems that indeed we have sort of different goals, and of course, if we have different goals, then of course we can use different tools and approaches to solve them. Then this is perfectly okay with me. And what's about Arthur has just said, I actually can disagree to a certain extent, because my point is that just biasing the search is not enough, because well, can you, for example, just by basing the search by searching only for small programs, be able to reconstruct a program for printing a million digits of pi? So it's a program like 100 bytes, but no method of direct, even biased search will not be able to find it, because it will require such an incredible amount of computational resources that we should have the limitation into account in any case.
Well, if you're talking about exhaustive search for through the space of all programs, biasing by their lengths, of course, at some point you will also be, or very quickly you will run out of resources. Of course, I do not think that exhaustive search bias by the length is enough. Of course not, because would be then we would be done with AGI, and if that was efficient. And there's more necessary, exactly, and you need techniques to more efficiently find those programs. That's exactly why we have built the incremental compression for. But beyond that, there's also more needed.
Yeah, but my point is that for any specific domain, you will have different search techniques, different biases, and even explicit solutions. Like, for example, if we are talking about Rubik's Cube, yes. If we are talking about Rubik's Cube, then yeah, you start with a sort of random search while you are trying to figure out what the algorithm is, but you cannot really efficiently solve Rubik's Cube without this algorithm. I mean humans, and that's why we specialize our general search. Yes, we have a sort of general search, but it's not just about bias in it. It's about the possibility to specialize it to particular tasks and to particular domains, because we have specialized learning procedures to this and so on. So yeah, we can say that well, on some abstract level, we have a sort of universal induction and so on, but it's a tiny part of the story, and that's why we are pursuing this cross-paradigmatic approach.
I think it's important to have several approaches going on, a cross-paradigmatic approach where many algorithms interact with each other. It's also a viable approach, but I think it's also important to have a different approach which tries some kind of monolithic approach toward the problems, the big problem to solve. And as for different domains and different algorithms for them, we have to take care whether they're really different because they are necessarily different, or they just happen to be different because different people came up with different algorithms. Like, let me give you an example. Let's say you want to train a decision tree, and then you minimize the Gini coefficients for your decision tree, and you do it stepwise, and then you separate the sets into more and more homogeneous ones. Well, you can view it as a compression process too, because a set of zeros and ones, or a list of zeros and ones, for example, where there are just a few ones and all the others are zeros, have a short description. They also have a small Gini coefficient. And the other thing you can say, okay, let's look at boosting algorithms, for example. Well, boosting looks at those part of data that the previous step is bad at predicting, bad at describing. And you can view it as a way of incrementally compress the data, because you look at the part that has still a large description, and then you take your little optimizer and treat it further. So there may be, of course, there will be domains where there are necessarily different algorithms, but the thing we have to think, I think, what is the major goal that they're trying to solve those algorithms? Are those different goals all the time? I mean, if these are different goals, is it all about intelligence then?
Yeah, I guess there are different goals. So what Arthur, you just said, I agree. And very often the difference is in the solution. It's for the same problem, you have multiple different algorithm as solution. Each has its advantage or disadvantage. And that's clearly the case, but that's not what I'm talking about. I'm talking about different goal, meaning that even if you see, Alexey mentioned, say, a cubic, Rubik cube, okay, and many other problems. Actually, there is a perfect solution. There are some algorithm we can follow step by step, especially for the games and puzzles. I don't know whether you noticed this phenomenon. As soon as there is a solution, it lost the fun. Okay, you don't want to play that game anymore because there is a procedure you can follow, perfectly solve it. That also is related to the so-called AI effect. That is, as soon as you find a solution to solve a problem perfectly, people typically say, it doesn't really need intelligence anymore, it just follow algorithm. Why? According to my opinion, that's very easy to explain. That's just from my definition. It's only when you don't really know how to solve it, this process really demands intelligence. If you have a perfect solution, and then that's just computation. You see, people usually think intelligence is better than computation. To me, it's the other way around. Computation gives you a perfect solution. Intelligence is what you use when you don't have a perfect solution. So that's one point I want to make. Another one, since also you mentioned Solomonov induction, I have to say I don't agree with that model as a model of intelligence. Actually, I explained that in AGI 13, I think. Marcus and Ben and me was in a workshop there talking about the probability theory and AGI. One thing you mentioned, I agree, that is what makes Solomonov induction attractive to many people is it takes a short description into consideration. People say that's one form of outcomes research, which is also take kind of like resource into consideration. But I think I mentioned in that publication, I think that's a very different interpretation to that principle, which I have to say I do not agree. That is, outcomes research in the original form just basically say that we prefer simpler solutions. I think in that part, no one disagree. Everyone say, yeah, simple things are better. But the problem is why simple things are better. Solomonov induction make the basic assumption that simpler things are more likely to be true by giving it a higher prior probability. To me, well, yeah, you can assume that. I just don't think that's the only possible interpretation. To me, it's either simpler things are preferred just because you don't have enough resource. Okay, you cannot handle more complicated things because you are short in time. So you prefer simpler things, but it doesn't mean simpler solutions are more likely to be true. I don't see any proof of that. I don't, in science, we also see that simpler solution doesn't necessarily have a higher probability to be true. But it's indeed the one we try first. Why? Because we're short in time. So I'm not saying that you cannot assume that, okay? What I'm saying is you should not take that as absolute truth. You have to say, that's my assumption. Under that assumption, I can derive a Solomonov induction, which I have a high respect. You know, it's an elegant mathematical work. What I'm saying is assumption is not always justifiable.
Well, I think
it's my turn. Sorry, it's my turn.
Sure. I didn't think there is a.
Let's go one by one. So first of all, I'll start with what Pei mentioned about fun to solve new problems. Of course, that's true, but the point is that in our daily lives, we have to solve recurrent problems. And for example, when you are learning to drive or to walk, maybe you put much more intelligence in this process. Not maybe, but for sure. Yes, but this skill which you have learned, it is not just thrown away after you form it, but you use it. So we don't need to solve just one example of the problem. We exactly our intelligence we needed to form these automations, to form these skills. So it doesn't contradict to my picture of how this nested partial order of solvers can be arranged in general intelligence. So you are just talking about the highest level, but this system should include all these levels. That's my opinion. And about Solomonov induction, of course, Arthur will answer as well, but there are actually formal and quite simple proofs that this should be true, although they may be not well known or maybe not precisely what you expect from them. Basically, if you take any measure, you can call it simplicity or whatever. And if you arrange your solutions using this measure, and if these solutions, the number will increase exponentially with this measure, and if you have no knowledge to distinguish between solutions of the same complexity, and this can be a different type of complexity. It even doesn't matter. It can be program length, execution time, as a mixture, whatever. Then if you want to get correct measures, then you should, in average, not necessarily precisely, but in average, assign probabilities which will be 2 in the power minus this complexity measure. And it will be true whatever measure you assign and whatever complexity type you consider. So it works in average for sure. But of course, there are some tricky details. I wanted also to say something about what Arthur was speaking about before pay, but I have already forgotten, so maybe it's Arthur's turn to continue.
Well, so there's a question related to this whole discussion of Solomonoff induction, and maybe it's relevant to everyone. What would be empirical evidence for Solomonoff induction? Another person said, is the neocortex an existent proof of an approximation?
Well, the thing is that that relates to what Pei has said and what Alexey has commented on. It's not like we have a choice of picking the Solomonoff prior or not, and it's a mathematical necessity. The thing is, it's a prior distribution over also all explanations of the world. Let's say it in a casual way. And a distribution, a probability distribution, or it's a semi-measure more strictly, has to be bounded, right? The probability distribution has to sum to 1. And if you have an infinite number of elements, but the most of them are long, the programs, most of the programs are very long. So if you assign to long programs high probabilities, it won't sum to 1 anymore. And so you have to assign the longer programs small probabilities, and that's Occam's razor. The long explanations will have to be a priori unprobable, and that's so that's actually a mathematical necessity, and it follows from Kraft's inequality essentially about prefix free sets, that it has to be bounded. So you can rearrange, of course, some of the programs and reassign different probabilities, but overall you have to have this Occam bias. So so in terms of the question how we can see evidence of Solomonoff induction in the real world, well, it's a mathematical necessity. Why do we need evidence for it? I think the question is maybe whether humans actually use it. Well, I think that evidence is overwhelming, that people actually try to pick more simple explanations over more complex ones. We can review. I mean, I can say something about the psychological evidence where you can see that. But yeah. I think that would be my answer.
Yeah, I think I will kind of like agree on both. First, we do prefer simpler ones. It's the same as in my system. It just what's the reason. The second part you say is necessary, as you said. You have to give longer one smaller probability, which is also true. But you didn't mention that's under an implicit assumption that you have to assign probability value to all hypotheses. This is something I don't feel convinced. Why do you have to assign a consistent probability to all hypotheses? And what makes you think at a certain moment you can list all possible hypotheses, even in principle? And at least in my model, I do not assume that.
Well,
Yeah.
okay, Alexey's turn, yes.
Yeah, first of all, thanks to the question, I recalled what I wanted to say to answer to Arthur's remarks, and actually they are relevant also to Pei's remarks. Basically, when you are talking about Arthur, you are focused on criterion, yeah. So what you were talking about was exactly about look, we need to compress and so on. So it's all about criterion. And well, I was working on the minimum description length principle and its extension, representational minimum description length principle for more than 10 years. And I was also very excited about how this criterion can explain a lot of things, and how can we use it to improve more heuristic methods which use sort of more heuristic criteria and so on. And what is missing here is something much more important. It's exactly computational aspects of how you do this sort of things. So when you don't consider these computational aspects at the same level of, for example, mathematical strictness as you would like to consider Solomonov induction as a criterion itself, then you will be lacking an important component, an extremely important component for AGI. So this computational aspect is also very important in the connection to what Pace says about if we can assign these probabilities, can we optimize them. First of all, I would like to underline that Kolmogorov's foundations of mathematics, of probability theory, don't use the notion of probability as a basic notion. It's a derivable notion. So it's not like we assign these probabilities. So we have an asteroid which is moving towards the Earth, and we say, look, it will hit the Earth with probability say 10%, and then we acquire more information and say, no, it's not 10%, it's 1%, everything is safe. So it's not a probability per se, it's our estimation of the degree of our uncertainty in terms of lacking knowledge and information, which is also connected to computational resources, because there can be quite complex models which we cannot just evaluate. And in this sense, we still have this implicit priors, as Arthur said, and I agree. It's just a mathematical fact that they are there, and we can not precisely use them due to computational resources, and that's also okay. Then we just will do not that perfect as possible. But if we are talking about the question from the community about evidence of Solomonov induction and so on, once again, I wouldn't agree that this evidence should be found in compression. It's obvious that sort of compression should be taking place, because as we consider Bayesian inference, information theoretic or whatever, anything, even fuzzy logic, it's just a sort of approximation of probability theory with certain statistical independence conditions and so on, then we will observe this. So for me, what's the most important thing in Solomonov induction is not a specific form of priors, because they can really be different depending on the reference machine, depending on the complexity measure, because it's, as I mentioned, can be not only program length, but computational time or the mixture, so whatever you like to choose. But what's the most important thing from which we should start is that it assigns, Arthur also mentioned it, but didn't articulate, we assigned non-zero probabilities in terms of we consider this hypothesis in principle, our system, desirable system, or most likely our human intelligence is arranged in such way that we don't reject any of these hypotheses a priori. And this basic starting point from which we can derive different conclusions. And the question is, if it is really so for human intelligence, so if we indeed don't have such limitations, if we can indeed come up with any hypothesis, and we are doing this not too well, but from my opinion, the whole history of science, the fact that humans invented universal Turing machine, that they can write programs, it's a sort of proof. So I don't search for the proof in neurophysiology, but it's enough, this argument is enough for me to say that yes, in this sense, we are universal and we correspond to Solomonov induction in a certain sense.
So there seems to be a pause there.
Are there further questions? I thought there should be, or if not, we can just continue on those topics or different topics.
Well, there is another question from the community, and I have another question that I'd like to end with at least. Oh, here's a, so there's two additional questions from the community. Is the choice of Turing machine for Solomonov induction really arbitrary, or can there be some Turing machines that are simpler than others?
So, Alexey, do you want, or I can do?
Well, as you wish, actually, I wouldn't like to make this panel discussion all about Solomonov induction. And that's an interesting question, and I can talk about it for some time. But I would like just to point out to Ben's paper on Occam razor. I'm not precisely sure how does it, what's its title? Just a second.
Well, there's another question if you prefer.
Grounding Occam's razor in a formal theory of simplicity. So I'm not saying that it's sort of final truth, but I think it's a kind of answer to the asked question, and it's an interesting stuff to read. So Arthur, maybe you can
well, the short answer is that the convergence theorem of universal induction is independent of the machine. It always converges. It converges fast. So it has better even proofs than AGI itself. So, but I agree that we shouldn't hold up ourselves with Solomonov induction only, and I mean, I could, for example, talk a little bit about various psychological evidences for how we can view various cognitive functions as performing data compression, essentially, or finding minimal descriptions. So, but I don't know whether it will, how many questions we have.
I think, sorry.
Yeah, sure, go ahead.
Yeah, I would just want to add, I also agree that we don't want to go into too much technical detail given this situation. But I think I pushed on Solomonov's induction before. It's just because I think it's a perfect example to show what I said. We are not really working on the same problem. Okay, so we roughly say, yeah, we all want AGI, but what that exactly means, we have very different assumption about what can be assumed, what is important, what is not important, at least at the beginning, as shown by our previous discussion. So with a better understanding about our difference, I think we can actually cooperate better. You know, if we are not working on the same problem, it's not necessary, you know, whether your approach is better, my approach is better. Well, they have some relation, but they're not really directly comparable in that sense, technically speaking. So that's my conclusion.
Brings us to another question that I was going to ask earlier, again from the community. Could there be different approaches? This was originally aimed at Alexey, but I think it applies equally well. Different approaches to AGI that are fundamentally incompatible with each other, which therefore could never be integrated into some sort of unified system that was being propagated or suggested by Alexey.
What is incompatible?
Pardon?
What is incompatible? I didn't get the question.
Could the different approaches to AGI be incompatible?
I think they are. From my previous answer, they're clearly incompatible at the fundamental level. Even though we can cooperate, we can do, say if we want to do one concrete application, we can combine several technology. But those theories, clearly they're not completely compatible.
Okay.
Well, I think it's sure, go ahead. Yeah.
Well, it's if this question was originally to me, I just would like to answer and not skip my answer. But if you want to go first, go ahead. Oh, no, okay. I can continue. So yes, I wanted to say that if we are talking about different AGIs like Pace AGI and Arthur's AGI, then there sure can be incompatible approaches. But if I consider one image of AGI in my head, then if I consider different approaches to this very same AGI, then I would say that they should be compatible, so they should be unifiable to a certain degree. They can cover different, possibly intersecting subspaces of this nested space of tasks, domains, and solvers, learners, and so on. They can be completely in different domains and be united by something on a top higher level, or they can form a sort of cognitive synergy with each other. But I'm sure if something is being used for solving tasks successfully, then it's one of the projections of AGI, and thus it has some image which from which it was projected, and thus they can be unified. Yes.
So my view of it would be that, well, let's say you have, Ben mentioned at some point that one of the core problems in OpenCog is inference control, and to find out which rule to use when, and to arrive at conclusions and not letting your search tree expand too much. So much of the inferences to narrow down in general are about noticing regularities in some sort of the other. And if you notice regularities, then you can continue searching in a subspace of all solutions that all have that regularity. So if you have a system that generally notices regularity, even if it does it below some complexity threshold, then it can be used as a plug-in thing to another AGI approach, for example, that helps out with certain to bias a search engine for inference control, for example. So that way, a prediction algorithm that we develop, for example, could be used in another AGI system. So, and I think there are some possibilities to help each other, let's say, but of course the paradigms that we have in mind differ significantly often.
Okay, and I think this will be the final question. And this is fairly open. This one's from Ben. So when you're thinking about AGI, what is one of the biggest unanswered questions you have about AGI right now, which is occupying your mind every day?
Well, Pei, do you want to start?
Yeah, simple answer. I don't have such a question. I have a whole bunch of questions in my mind I'm still working on with respect to NARS. I don't have one big question in my mind.
Okay, so it seems we will go in a reverse order in comparison with how we started. So let me try answering this question. Actually, indeed, there are too many questions, but in the context of what I've been talking about during this session, well, every day, I would say I wake up with the question, why there is so much sidetrack research in AGI? Why just we don't look where we lost the thing, but look where it is bright. So indeed, the largest, the biggest unsolved problem may be how to do an efficient yet general inference. It's well, not necessarily about universal induction. We can consider it in the context of probabilistic programming, logic, in even deep neural networks, and so on. Well, when I answer this question to myself, I recall that it's just impossible to achieve such efficient yet general inference. And what can we then do? Well, I would not like to give up on this idea of efficient and general inference, yet I would not like to just do a sort of universal induction. Well, as I described, we have a sort of nested methods for inference, for search, for problem solving, for learning, and so on. And once again, like we have just discussed, there is a sort of confusion. So, for example, humans cannot calculate well. They cannot beat AlphaGo, but they can develop it, they can train it, that then can use it to make better moves. AlphaGo calculator cannot control humans, at least just in the same way as we can. So the question may be, are all these problem-solving methods are just internal tools which are similar to external tools like calculators and so on, and maybe intelligence just managing them. Maybe AGI is much more simple. I mean, not simply designed, but not that universal and so on. And what makes it powerful is just the use of these powerful tools. Maybe universal induction, deep learning, and everything else are just optional tools for something else. If so, then what from fundamental principles should such intelligence be derived. But I actually don't believe so. I guess that this top-level tool user is quite similar to all these lower-level problem solvers, and it lives in the same space with them. So the first biggest question here is to represent the space of problem-solving, inference, learning methods, and so on. So it will span everything from AGI to explicit solutions of narrow problems. So what is the structure we should impose on it? And after answering this question, I guess we can make a small step closer to AGI.
Well, I wouldn't say there's a certain big question that's bothers me. I mean, maybe the biggest is the same as Alexey mentioned, the problem of general but efficient inference, but it also breaks down in many other questions. For example, I think what is the source of meaning? Well, how do words acquire meaning? Is it some partial description of the actual object, or how do we make descriptions less crisp, like only vague, capturing only sort of something like the first principal component of that? The other question also Alexey mentioned, how we will deal with specialization, how we derive algorithms that are good for special problems, how to automatize that specialization. Then I think about cognition. Why is perception so fast compared to multiplying numbers or so in humans? Why do we have these biases? How did these biases arise? And how does memory work? How do we have a graph inside our head that tries to, how is it organized so that it can at the same time forget things that it doesn't need, that have been long ago or did not serve us well? And how do we enforce the parts that are useful? How does their description dynamically change so that we can find it more easily when we have encountered it more often? And then I think about what can we learn from neural networks, for example. I mean, it's obviously great that we have good optimization techniques so that we can just minimize a certain function, do gradient descent, and but there's much more to it. Instead of how does these statistical let's say continuous approaches relate to the discrete approaches where you have many combinations? Can you apply the continuous approaches? Can you, for example, make a neural network that by itself certain functions crystallize, like multiplication, taking a power, and taking a square root or so, little operators that pop up as little modules of neural networks that can then help the neural network to do really to approach the problem of AI in a more algorithmic fashion rather than in a curve-fitting fashion, let's say. How can we achieve that? How can we achieve compositionality, for example, in neural networks out of distribution generalization? How can we build systems that take up less data and lead to more one-shot learning? What is it related to? And what is the difference between causality and correlation mathematically? Or how can you pinpoint that? What is actually causal? Is it the correct representation of the world that makes it causal in some sense? Or I think discussions about this have been quite vague. Why are the systems not so interpretable, and so on? I mean, I could go on a lot, and I think in my mind I have a big soup of all those questions that pop inside the mind in a quite unregulated and seemingly random fashion. And yeah, I sit and sometimes I figure something out. Sometimes I have no idea, and yeah, that's what happens in my case.
Sounds probably very similar to Pei's many questions.